Okay. Go mute. Okay. Test, test, test. Okay. Now it seems to be running. Okay, good. What is also interesting, last week, before I went to, during the holiday, when we had the Monday holiday, I was in Korea at the FIRA Invitational Cup. That's organized by the city mayor of Seoul, and the top three teams from the FIRA World Championship were invited to compete there, and my team was there. So we did quite well. We won one first place, one second place for overall in the all-round category, which is like the Kings class. So I'm quite happy about that. They also had the humanoid conference going on at the same time, where they had um, uh, the Unitree G1 robots there by Unitree. They were one of the industrial exhibitor. And we also had one team competing with the Unitree G1 robot in the competition. Um, and actually, that robot would be like you can see that's state of the art for the robot, right? There's nothing like it in the world at the moment. Certainly not something that the research lab would be able to develop. But it didn't actually win, and the reason for it is that Unitree has two different versions of this and the software. So the one that they sell to universities, I talked to the professor in Korea. A lot of the source code is actually hidden away inside of the embedded systems that they use. So you cannot actually modify the walking engine. You cannot modify the low-level behaviors. So the Korean robot, the Unitree G1 from the Korean professor, and the robot that they demonstrated at Humanoids, you really think is two totally different robots. Like one of them does flips and back kicks and everything, and the other one is a good robot, but it kind of walks like this. And it does some push recovery and everything. I'm sure we didn't actually get to see that, but it feels like a much lower quality version than the Unitree G1 robots that they demonstrate. So I think, and the professor told me one of the problems is that they don't have access to the lower level behaviors, so they cannot modify the. It only gives you that one safe walking gait where you can change some of the parameters, like foot height and step length and things like that. Those you can modify, which is a pretty standard way of modeling the walking gait of a human, of being able to generate different walking gaits for a human. Um, But anyway, the humanoid conference was pretty interesting just to see that robot live. They didn't do the backflip, but they did do like running stars and things like that that can work pretty well. The other thing that we have that the difference between robotics and AI is that if you do have a bias in your system, then that will usually it will be very bad for your robot system. And the AI systems, because they are working on in more abstract, complex spaces, like if you're a humanoid robot, if you tell it to go forward and it always turns right, then you would notice, right? That kind of bias. But in the abstract spaces, it's not so easy to even recognize that this is happening, and because we're using AI systems now more and more for day-to-day lives, these biases can also be very hurtful and problematic for people. And in fact, most of them would be illegal. So just today, I heard from a paper that was done by some professors in Germany, and the history of Germany. Germany was divided after the Second World War, taken over, split into sort of the Western region and the Eastern region that belonged to East Germany, which belonged to Russia, was associated with, aligned with the Soviet Union. Then, when the Soviet Union fell in 1990, Germany united again. Right? That's history. So there's the Western provinces that have had rapid rapid economic development, much more rapid than the eastern parts. And when the researchers now looked for biases in ChatGPT and all the large language models between the Western provinces and the old Eastern provinces. So these are called East Germans and the West Germans, based on that historical division that was united in 1990. And it was extremely interesting. So the system, basically, when they asked it for the different provinces in Germany, the ones that were Western, the ones that were Eastern, they would ask it, how industrious are the people in Hamburg? How industrious are the people in Munich, which are the Western? How industrious are they in Sachsen-Anhalt, which is Saxony, different province? And the system would give the East Germans always lower scores. So industriousness, honesty, intelligence, everything, right? If you ask the system, it would say yes. There's like IQ is whatever 98 in Western Germany and 95 in Eastern Germany, which is clearly discriminatory, right? The other thing that they realized was that the system was actually not consistent. So they asked it which province is more industrious, this one or this one, or how industrious are the people in the Western province? Then they would give a higher number to the West Germans, lower number to the East Germans. If they asked it who is more lazy, then it would also give a higher number to West Germany, lower number to East Germany, even though those two statements cannot be true at the same time, right? But it doesn't realize this contradiction. So basically, whatever it did, it would give a lower number to East Germans. And that even went as far as they asked it, what's the average body temperature? And what's the average body temperature? Huh? Yeah, in Fahrenheit, yes. We do Celsius, yeah. 36.5 to 37.5. But that's true for basically everybody in the world, right? There's no no difference in body temperatures. It would still give the East Germans a lower body temperature than the West Germans. And so this means that particular bias is permeating all the data that it had. Basically, any question that you asked about East and West Germany, it will give you the same tendency. It's completely illegal, completely irrational, right? There's no basis for it, and very discriminatory. But I thought it was funny to just ask it, what's the average body temperature? And it would just say, oh, East German's definitely lower. Now, I tried to repeat that with ChatGPT now, but it didn't give me different body temperatures for. I asked for Canadians and Americans, so see what one. It said no, they should have both the same body. Let me see what you. Good. So let's talk some more about. So your job. So your job for the second assignment would be basically this. You get a picture. Climb this. No. You get a picture of the climbing ball with the different holes, and they will be color coded, three different types: red, green, and blue. And that will mean that the holes are in a particular orientation. I think here these are actually all the same. It looks like I don't know exactly how the speed climbing competition works, how they do the routes and stuff. But you will need to figure out the position of each one of those holes so that you can pass it on to the planner, so that the planner can figure out which way he wants to move the arms and the legs. And then on the planner, you can work together with the students from the humanoid robotics course and the students from Germany. Then the humanoid robotics students will be working on actually building the robot to climb this. A small version of this, and small humanoid robot, not this size. So it would need to be some kind of probably correlation based or other based detection, object detection algorithm, followed by the calibration so that you get real world coordinates. Like the first step would be to find these things in the image, and then figure out where they are in the image, but that only tells you where it is in respect to pixels, right? You need to tell the robot where it is in real world coordinates. So that means you need to calibrate the camera. And so then that's what we'll be talking about today. Okay. Okay, this is all still running. So what we're dealing with, the actual problem definition is that I want to be able to come up with a method that allows me to map from 3D world coordinates to 2D pixel coordinates. So that tells me where a pixel in the real world will appear in the image. Right? And then the inverse. However, the inverse is undefined. to map from the image to the real world coordinate, actually, that's impossible to do that without some additional information. Because if you think about some point here in your image, right? Where you see it in the image, that only establishes a line correspondence. It tells you which line that particular point is on, but it doesn't tell you how far away it is from the eyes. Right? So you need some additional information to be able to do that. And there's many ways of getting that, for example. So one way would be in robotic soccer, when we're detecting the position of the ball, and I need to know how far that is away from the robot, then I need to know what the pan and the tilt angles are, right? Where I'm looking at. And then, if I see a ball at a particular pixel location, then we assume that the ball is on the ground. Then I can establish the distance from I can intersect that line with the ground plane, then I know what the real world coordinates are of the ball, right? And in the case of the climbing wall, what can we do? What kind of extra information could we use in order to establish distance from the robot to the wall? Well, if you know this distance, for example, or the height of the wall, then that would give you one extra piece of information, right? Then you would be able to establish the distance between your robot and the entire wall. Then you can put the pieces in there, the holes. You can also use these little dots here. If you can detect those, then you can figure out, those are standardized, so they're always 20 centimeters, then you know how big the entire wall is. But you need some extra piece of information. But if you know the 3D point, so if you know the distance, x and y and z of that particular point, you can always map it back to the image exactly. How do humans work in the three-dimensional world then? How do we establish the distance of objects around us?
From both eyes.
Yeah, we have two eyes, right? So we actually get two lines. Where those two lines intersect, that's the position of the point. So that would be a stereo vision based approach. Right? You can use two stereo vision, then you can establish the distance always. Now, what's interesting is that lots of optical illusions actually are based on the fact that people think that their stereo vision is working very well, but actually it's, for example, that door, if you look at the parallax shift between the right eye and the left eye by closing one eye, it doesn't really jump that much. So your brain really cannot tell distance from here to the door using the two eyes. So how do I know the distance to the door? I don't. And human people usually don't have to know that. But I do know the average height of a door, and that gives me sort of a ballpark figure on how far away I am. And for most day-to-day living, that's sufficient. Nobody asked me to measure or to get the distance to the door within centimeters or something like that, right? Stereo vision works mostly for things that are within arm's reach. So if you're trying to thread a needle, like the needle and a thread, and you're trying to push them in, both very small, that's where you use your stereo vision. I actually did an experiment while I was in Korea with the latest teleoperated robots by PAL Robotics. And now a lot of the manipulation now has also turned into a very hot topic in robotics, in particular dual arm manipulation. Because in order to do anything useful in a factory or in the kitchen, you need to be able to move objects. And that's another topic where robots are not very good at the moment. So there's a lot of research in that area. One of the ideas is are these digital twin kind of things where you can sit, and PAL Robotics has this system. You can sit there, and you can grab the and it's like a robot arm. You can grab and move them around very easily, and then there's a big robot that follows your movements. And then you can press a button, then the gripper closes, and you release the button, then the gripper opens. The one that they were demonstrating there didn't actually do any force feedback. The more complex system try and provide you with some idea of now I'm hitting something, so now there's some force acting against me, or I'm trying to lift something heavy. That was really quite, it was easy to use one arm to pick up a Lego block. They had these different Lego blocks on the table, and then you were just playing with the Lego box. But I was sitting here and I could see the table and the robot arms, so it wasn't a virtual reality set. So the robot was maybe there where those two monitors are. And from that distance, I basically, even though you can move the two arms together and then the two robot arms come together, to put one Lego block on top of another, the way it's supposed to, like to stack them together, I basically failed. I wasn't able to do that because I was always slightly off in the distance between the two Lego blocks. So on that distance, my human 3D vision didn't help me. If my 3D vision would have been 100% accurate, very finely tuned, then I should be able to do that by just looking at it, right? But that you can't. Maybe some other people can, but I certainly can. And I consider myself, my perception to be reasonably average, even though I need glasses. So here, the way I have it set up is previously we talked about homogeneous coordinates and rotations and translation matrices, right? Did we? I think we did. Yeah. So just a refresher then for homogeneous coordinates. And the camera model that we're using. So we have an image plane, and this is called the pinhole camera. There's a single point to the camera. Mathematically a single infinitely small point. And then we have some object in the real world. Some tree, and I want to figure out where that tree, what happens is some light gets reflected from that tree and then goes through the pinhole and then hits the image plane on this side, right? And this is what your camera records as the image. That's what it spits out as a JPEG or EMG or something, or raw image. And this particular point here if this were a straight line, then it would show up on the image data. So that's what our camera does. A couple of definitions or terms. The point 0, 0, or the 0 point of the image plane. This is drawn here in just one dimension, but of course your image will be two-dimensional. Like, it's not just a single line, it's an actual plane. That's what gets you the image. That will be called the optical axis. And the point, that particular pinhole, is in front of the 0, 0 position of your camera. Right? So this here will be a 90-degree angle. And the distance between the image plane and the pinhole would be called the focal length, F. F or lambda, both of them are used. So now we'll draw that again, just in more detail. So this will be F. Here I have an image coordinate, U. Here is my optical axis. And here I have some point that has coordinate X. And its distance is Z away from the camera, from the image plane. Okay. So then, or before we start with this, how can I actually position the camera in the world? Like if you hold your mobile phone, right? And you start, and now my phone is at 0, 0, 0. Right? We'll just call that origin of the world coordinate system. Now I want to take a picture of this particular area here. That's where the playing field is, where the robots are playing. Then what actually happens to the camera? It moves, right? But what kind of movements are we actually doing? I can shift it, right? I can shift the camera X, Y, and Z, right? But I can also rotate it. So with the camera, we can translate it or we can rotate it. So now if we translate points, okay, let's do it from scratch. So I have a three-dimensional coordinate system, like we're working in 3D. And now I want to figure out what the new coordinates are if I move things by translation of tx, ty, and tz. So I can shift things in the x direction, the y direction, or the z direction. Then our new coordinate for x dash would simply be x plus tx. Right? And the original y plus ty and z plus tz. Right? Okay. Now, I already mentioned that computer vision, computer graphics, certainly in the early days and still today, a lot of very strong mathematicians are in that field. So mathematicians like to keep their things tidy. One thing that they like to do is for these kind of systems of equations, right? These three equations are connected, and they're connected with simple linear terms. They like to convert them into matrices, matrix representation. So then, if I want to write this in matrix representation, then we have a problem, because here we have tx, ty, and tz. Those are actually constant. They're independent of x and y. So here I want to have some kind of matrix that takes x, y, and z as the original coordinates on the right hand side, multiplies it by a matrix, and I get the left hand side. But here I have tx, ty, tz. So that doesn't really work with a matrix. Like I could do x, right? I can get the x by saying 1 times x, but then 0 times y, 0 times z, okay? But the plus tx is a problem. So that means we need to have in order to incorporate a constant term, we need to have a 4 by 3 matrix here. And that would work, but then 4 by 3 matrices are not square, and mathematicians don't like not square matrices either. And in a second, and so here, in order to get that constant term, I also need to put in a constant. Now I could put any constant in here, right? I could put k here, and then this would be just tx divided by k. But the most natural one would be to use a constant of 1 here. And now that would work. Now I get x dash is equal to 1 times x plus 0 times y plus 0 times z plus 1 times px, right? Y dash is 0 times x plus 1 times y plus 0 times z plus dy, which is the second equation. And the third equation, z dash is 0x, 0y, 1z plus dz, which is our third equation. Right? Now, this representation, one thing that we did is I added this 1 here to the point in order to give it a constant. So this is called homogeneous coordinates then. And we end up with a 3 by 4 matrix. Now, because of camera calibration, or we've now what I would be able to do would be to move the camera in the world, right? I could translate it. Actually, so far I can only translate it, but I'll show you in a second what the matrices look like for rotation, or you've probably seen them already, the 2-dimensional, 3-dimensional rotation matrices. I can also represent rotation as in matrix equation form. So that means I can move the camera around and I can align it, I can rotate it around some point. The one thing that I cannot, that doesn't allow me to map from 3D worlds to image coordinates yet, because the effect, because of the perspective distortion or the perspective transformation. If I have a point here and it looks this big, if it's further away, then it'll be smaller, right? That pen. So that effect happens in the human eye. It also happens in the pinhole camera. If you look at it here, that's why I cannot tell the distance, right? I have this point and this point, and both of them, so this point here would have coordinates x and z, and this point here would have x dash and z dash, and both of them would be mapped to u. Both of them result in this pixel being lit up. Right? So, how can we model this perspective distortion? So how can I figure out what is u? I want to know what is u as a function of x and z. Now, in order to solve that problem, we need to look at the geometry of the problem, and then we can establish two triangles. I have this triangle, and I have this triangle. Now, if we look at those two triangles, then what's special about them? Yeah, they're both right triangles. More than that, what about these two angles here? They must be the same, right? So that means that we have one right angle here. We have these two angles which are the same, which means that because all the angles added up together in a triangle must add up to 180, that means these two angles are also the same, right? So that means all three angles in the triangle are the same, right? And so that's what's called, if you paid attention in high school, you may remember that this is called similar triangles, right? So these two triangles are called similar. So why is that important? Similar triangles have a specific property, or it's true, you can prove that for similar triangles, the ratio of two sides is always the same, it's constant. So that means that this triangle here, if I write it down for the one that I'm interested in, that will be u over f, right? U divided by f has to be the same as what are the corresponding sides for this u? What corresponds to u in the green triangle? X, yeah. And what corresponds to f? Z almost. Huh? It won't be z except this f part, right? So it'd be z minus f, right? So now we can reformulate that. I can multiply it by f, and then I get u is equal to x f z minus f, and I can also divide it by f then. And I would end up with this. U is equal to x divided by z over f minus 1. Right? Which is simple arithmetic manipulation of this to get that. Okay? And now we have this equation here. So when I think about the camera system, oh, yeah. When I think about the camera system, then I can do all the translations, and it's clear since I have this in a matrix form, right? If I now do one translation first, then I get the new coordinates from the original coordinates, I multiply by some transformation, I get the new coordinates coming out in the left-hand side. If I now do another transformation, then I have to left multiply the next one. So I can calculate compound transformation matrices. And later, in a second, I'll show you rotation, but it could be either a translation or a rotation. Let's just call them compound matrices A. And then if I do something like first I translate by Tx, Ty, Tx1, Ty1, Tz1, then I translate again by Tx2, Ty2, Tz2, then I rotate by 30 degrees around the x-axis, then I can calculate the matrix multiplication of all of those matrices to get one matrix that represents the cumulative effect of doing all of these transformations in series. I have to be careful because I must multiply it on the left-hand side, because matrix multiplication is not what's called commutative. A times B is not the same as B times A if A and B are matrices. It's usually not the same as A times B is not the same as B times A in general for matrices. For integers, it is. 2 times 3 is the same as 3 times 2. So integer multiplication is commutative, addition is, but matrix multiplication is not. So we must be careful to multiply these on the left-hand side. And then, at the end, I want to deal with the perspective distortion, right? And let's call that matrix P. And I can then, after I do all the rotations, translations, then I apply this perspective distortion, which is this pinhole camera effect. So what I have to do, if I look at this equation, right, then in order to get my image coordinates, the u-axis would depend on x. It's the x that I get from doing all of this. Right? I get some x, y, and z. So it's that x, and then I have to divide it by this divisor here, which depends on the z coordinate of that point, right? And it depends on the focal length, and then there's a -1 there. So basically we have to take x, we can do the compound operation, then we have to divide it by something that depends on z. Now homogeneous coordinates. So far we only talked about one as an extension here to get the constants for translations. Actually, homogeneous coordinates are, mathematicians defined them more generally as just saying that we have kx, ky, kz, and k. So I could have now multiple representations for the same point. So if I have a point 2, 4, 6, 1, then that would be the same as 4, 8, 12, 2. Right? Would be the same as -2, -4, -6, -1. Those three homogeneous coordinates are all the same point, 246 in XYZ order. That's just how mathematicians define it. But it turns out that that is actually quite useful in our case because what I have to do um, with my perspective distortion, with my P matrix, I now know what the P matrix looks like. Because if I use homogeneous coordinates, then my P matrix would be for x would be 1, right? Which will give me this x. And now lastly, I need to represent that. Right? So that will be 0, 0, 1 over f minus 1. Because in homogeneous coordinates then here, uh, this term will be z divided by f minus 1, which is the minus 1 I think there. Now this will be my k. In order to get x then, I have to take this x and divide it by this component here. If I now have a homogeneous point, x, y, z, 1, then it will calculate exactly this. Right? So we can model the effect of a pinhole camera in homogeneous coordinates. If I use the generalized version of it, then my matrix P will just look like that. So that means we have A1, A2, A3, A4 all the way up to the end until then I multiply it by P. Then I get those two, and boom, now I can calculate what the image coordinates are, the pixel coordinates. So that's, in theory, all that we have that we need to do. For completeness, does anybody know the rotation matrices? Yes? Okay, then what are they? If I have a point and I want to rotate it in the xy plane, then I usually do a very nice job explaining this, but I want to finish camera calibration today. I go through the proof of it, but it will look like this. Sine theta, cos theta. So here I want to rotate by an angle theta. And z coordinate is not changed, right? Now, here I need a 4 by 4 matrix. So we want to have square matrices. So we make all of them 4 by 4 matrices. So here we add an extra row of 0, 0, 1, and here as well. And then by flipping the axis, you get the other rotation matrix. They all look like this: cosine, negative sine, sine, cosine. Right? So this would be rotation along z, and then there is another 2 for rotation around the y-axis and rotation around the x-axis. And now, basically, we could calculate the image coordinates of arbitrary 3D points, because let's say, and there's some interesting applications for that. So, for example, what you projection mapping, it's called. You can do stuff like that. So you can do this, like you can have an LCD projector, and then you can project these kind of graphics onto an arbitrary 3D object. So when they did it, it looked actually really cool. Yeah, like this. Because in order to project that onto not a flat screen like here, but onto a 3D car, I need to know what the transformation matrices are. Now, if you want to be able to do that, and that looked kind of cool, I think. Then people already have problems with the BMW. And should. Here they did it on the Louvre. Right? So in order to be able to do that, right, what I would need to know is, I would need to know the matrix. So we could go to, where is that? Is that, looks a little bit like Buckingham Palace, but not quite. Let me find one that actually, oh, Statue of Liberty. Yeah. Oh no. I don't know. We could go to the Louvre. They could say, okay, we want you to do this projection mapping. Then I tell you that I need the matrices, and then what? Or if we do it small scale, or if you need to detect robots on the playing field, then you would go and you could measure the distance from the projector to the building, right? Or to the playing field. But if I do that and I ask the four of you to go and measure this, I'm guaranteed to get four different answers. Right? And then I ask you, okay, but I also need to know the rotation matrices. Then it becomes even more interesting, right? Because it's easy to use a measuring tape to measure linear distances. Getting angles is much harder. You can try and put your phone on the LCD projector in order to get the angles with gravity, something like that maybe work, or you would have to mount a laser pointer and then look at where the laser pointer hits some object that you know about. But it's a very error-prone process, right? So in practice, we usually don't do that because it's extremely error-prone. And what we know is whatever we have here, I can do the mapping exactly correct if I have this matrix. The only reason why we do the measurement is so we can calculate this matrix. But the matrix is really just 16 floating point numbers, right? So 16 unknowns. If I can find those 16 numbers, I don't need to run around through Paris with a measuring tape. So that's what's called camera calibration. If I know what the real world coordinates are and I know where that is in the image, then I can calculate backwards what the actual matrix is. And that's what we want to do today. So instead of using the Louvre or something, we're going to use the Rubik's Cube. And I just took a picture of the Rubik's Cube. And then I assigned a coordinate system to it. So I said that the origin would be 0, 0, 0 would be here. This is the x-axis, this is the y-axis, that axis is going upwards. So then I can sort of create a table where I have pixel coordinates, u and v, which is the x and y in the image, and real world coordinates, x, y, z. So then, for example, the blue point here, and I kept it as a constant. So let's say I don't know yet the exact size of the squares here. Right? I don't know the total size of the squares. Then this particular point here has coordinates 256, 200 in my image, and the coordinates, the real world coordinates would be half of the x-axis, half of the y-axis, like 1/2 square. So dc over 2, dc over 2, and the height of it, the z coordinate, would be 3 times dc. And the green point would be here. So the green point has a coordinate in pixel, 264, 460. Its x coordinate value here would be 1/2 square, like the center of this. The y coordinate would be 0, because it's on the front plane. And the z coordinate would be dc over 2. And the blue one here would be 245, 461. The x coordinate would be 0. Y is dc2 and dc over 2, and z is dc over 2. So I measured the size of that cube. It was 1.9 centimeters. So then I just generate a point of array, an array with these points. Points. So here I selected 6 points so far. And the coordinates that I found for them. So those I just selected manually. You could also implement the computer vision algorithm to find the center of these areas. Actually, maybe should have done that. So for the pinhole camera model, the image plane is mounted kind of like the back of your eye. In front of the plane there is a single point. The distance weighs f, and the lens so far is modeled as a single point. In reality, of course, it's not just a single point. It's a small area with a lens, and that means for real cameras, there's some additional distortions that you need to worry about. But we'll see, even this simple model works quite accurately. Light reflected from the object is going to go through the point and then hit some point on the sensor. So similar triangles, if the 3 angles are the same, and then 4 similar triangles, the ratio of any 2 sides must be similar. And I guess that's easy to prove, right? Because it's a right angle triangle here. So in that case, it will be trivially proven because what is u? If this angle here is alpha, right? Then u is equal to or here tangent. Tangent is opposite over adjacent, so tangent of alpha is equal to u over f, opposite over adjacent, which must be equal, because it's the same angle, so that will be the same as x over z minus f, right? Which is what we use in order to get this equation here. So actually we don't really need to know the similar triangles, because not only are the triangles similar, one of the angles is also 90 degrees, which makes the approach that we need. So here's another view of that. So I have a point here, focal length u, pz, the distance of that point. And then here we get different points in the image plane, u1 and u2, and different U2 and P1 projects to U1. So if I extend it, then we end up with UP. Now the difference is where I started that. Now there's two ways of writing the perspective distortion. This one here, I use ZP, which is the distance from the focal point to the point. Otherwise, it would be Z minus F. So scaling in homogeneous coordinates, U is homogeneous coordinates, taking our three-dimensional point and extending it by some constant k, multiplying it. And we end up with the perspective distortion matrix like this. If we don't take the, depending on how you define the distance, that's the difference here. That's if your distance starts at the pin as opposed to the image plane. Here I did it for the image plane. The distance to the point is Z. As you'll see, it doesn't matter which way you multiply or which way you calculate Z, because we're calibrating these values. Now, one thing that you will have noticed is in this particular model here, if I draw it like this, then if my point, this is x, so here x is positive, here x is negative, right? But if the point is here, it's going to project over here somewhere, right? So the sign of the x coordinate is going to change. Positive x will have negative u here. Right? Simply because if this is x positive, it's going to flip it around. So one common trick that people use when doing camera calibration, things like that, is instead of having the focal length, the image plane in front, the point in front of the image plane, which is physically how your camera, this is what your camera really looks like. We can put a virtual image plane at a distance of f in front of this point here. And in that case, the ratio is going to remain the same, and the sign is going to remain the same. So sometimes when you read computer vision papers, then they actually use positives there instead of a negative, and then they simply assume that the camera image plane, there's sort of a virtual image plane that doesn't really exist, which is in front of the focal point, just to avoid flipping them over. And then, one more. That should be a 0 here. And then whether it's minus or plus depends on how you want to see the distance there. So this is our perspective distortion matrix. Now, we know that our camera transformation is some kind of compounded transformation that consists of rotations and then translations and then lastly the perspective distortion. And assuming that I now have a set of calibration points, the points that I know where they are in the image and I know where they are in the real world, then if I apply those to this unknown transformation matrix, so here I have 16 unknowns, A11, A12, A13, because it's a 4 by 4 matrix, right? So I have 16 unknowns, then for every point that I have with these coordinates, I actually get two equations. First one for U1 is UI is A11 multiplied by xi, A12 yi, A13 zi, A14, which is the first row here, right? That's multiplied by x, y, and z, and 1. And then I need to divide it by this constant factor here, which models the perspective distortion. So A41 times xi, A42 times yi, A43 times zi plus A44. And that would be the rows of your image, and then V would be the columns of your image. So that would be this row here, the second row divided by the fourth row. Right? Now, how come I only have two? What happens to this row here? A31, A32, A33, A34. Here I only have two. What happens to the z coordinate of the image plane? That one I don't even need to calculate anything because it's an image plane, so I know that the z would always be 0 for the image. It's always where the sensor is located. So that third part would just collapse to 0 being equal to 0. So then, these are the equations here. Now I can reformulate it because right now I'm writing it with xi's and ui's, and the unknowns that I'm really after is A11, A12. So I can multiply by this row, which gives me ui multiplied by the divisor is equal to this, and vi multiplied by the divisor is equal to that. Then I can bring it all over to the left-hand side, which now gives me a set homogeneous system of linear equations. The unknowns are A11, and they're all just multiplied by constant numbers, and that all, every time it'll be equal to 0. So then I can take all of these points, and I can convert them into a large matrix here. X, Y, Y, I, Z, I, 1, 0, 0, 0 for the second row, and then negative xi ui, negative yi ui, negative zi ui, negative ui. And here, these will be the unknowns, the 16 unknowns, A11 to A44. That multiplied is equal to 0. So now I have a system of linear equations that models the camera that I'm trying to calibrate. Now, one question is, how many points do I need? How many calibration points do I actually need? Well, for a system of linear equations, if I have n unknowns, then how many equations do I need to solve it in general? Huh? N equations, that's right. N linearly independent equations, technically. So if I have n points, then n unknowns, I need n equations. But here, the number of unknowns that we have, because A31, 32, 33, 34 just gives us a trivial solution. So that's actually cut out. So I don't really care about that one. We reconstruct this part later on. So these four unknowns really don't matter. So I have 12 unknowns, but each unknown gives me two equations, right? One for ui, one for vi, which means that in order to calibrate the camera, I need to have at least 6 points. So if I can measure 6 points in the real world and figure out where they are on in the image, then I can calibrate this transformation. Now once I have that 4x4 matrix, then of course I can map from points, 3D points to real world coordinates, from real world coordinates to image coordinates, and with some additional information I can map image coordinates to real world coordinates. So we need to find not any solution, because of course if A11 up to A44, if that's all zero, that equation is going to be true, right? Because 0, 0, 0 multiplied by anything will be 0. But that's a trivial solution. That's not the one that we're interested in. We want to find the null space of this homogeneous, what's called the null space of the system, homogeneous system of linear equations. And the null space is usually not unique. If I take all the values in that matrix, multiply them by 2, I end up with the same relationship between the points. So we're simply forcing normalizing it then to have to get a unique solution. We pick the one where the size of the matrix is 1. So the norm of these vectors here, we set that norm to 1. So we have 12 unknowns, we need a minimum of 6 points, since each point gives us 2 equations. But in reality, to make this work, because every time we measure a point, there will be some noise, some error. Usually you need to have at least 15 points. At that point then, you have a least squared error approximation problem. You have an over-constrained system. So there's not one unique solution anymore because of the noise introduced by the points. But there's a very cool trick, Penrose-Moore pseudo-inverse method, which allows you to solve over-constrained systems of linear equations. And the original version of that equation would be A multiplied by X is equal to B, right? X will be the unknowns. A would be the matrix that I create by doing this, right? This would be my matrix A. This is X. And B, in this special case, would be 0. Vector of zeros, 12 zeros. Now, if I have less than 6 points, it's not going to work. If I have more than 6 points, then usually it's not going to return just one solution because of the noise. So if I now pre-multiply, and this is one of my favorite tricks with linear systems, if you pre-multiply that matrix by the transpose of itself, and then solve the resulting linear system of equations, then the solution will be the least squared error approximation. So the solution that minimizes the least squared error for the over-constrained system. In order to solve that system of linear equations, we can calculate the singular value decomposition. That's simply a way of actually doing this for a case of many, many different points. So then here's the code to actually calibrate the camera. To solve the matrix, we calculate the singular value decomposition, and we take singular value decomposition, takes a matrix and breaks it down into product of three matrices. So any matrix using SVD can be decomposed into a product of three matrices. Matrix U, which has norm of 1 for each column, and it's a set of eigenvectors of the matrix M times MT. Sigma, which is a matrix that contains all the eigenvalues of both MT and M, and MMT. And V is the unit length eigenvectors of this matrix MTM here. And if you look, this is what I want to calculate here, right? I want to calculate ATA. And the solution for that would be the eigenvectors of unit length. So SVD gives me exactly what I need. So I don't need to use any other. And it's more efficient than calculating the inverse that we would need to do or any other kind of solution algorithm for the original system of linear equations. So we calculate the singular value decomposition, and then what I want is the last row, the last column of VT, which would be the same as the last row of V. So the actual calibration of the camera is really only these three lines here. This point here takes the points and generates my matrix A. And then we calculate the singular value decomposition of this matrix A. And then the solution is the last row of matrix VT reshaped as a 3 by 4 matrix. Because the last row will have 12 entries, but it's a 3 by 4 matrix that corresponds to the calibration. So then, I can now implement a function that, given this calibrated matrix, I can pass in x, y, z coordinates, and it'll return the image coordinates of this point and x, y, z. So I simply need to multiply that point by this matrix A using perspective distortion. So we need to divide it by the second entry. And then here, I just have the algorithm to actually draw the figure for this particular cube. So this just draws the mesh over it. And then we can have a look at the output. And as you can see, I now trained the system. I calibrated the system for just these 6 points here. And I picked the coordinates by hand. And as you can see, the calibration is sort of okay here. It looks pretty good here in this area, but it's very poor here. There will be a large error there. Also here, there's a big error. So this calibration is not what you would want to do in practice. But there's many ways in which we can improve that system. Way one, all the points that I selected here were clustered in this corner, right? So I don't actually have any information about the points here. So that's not optimal. If you're trying to calibrate an object, you're trying to get calibration points over the entire image plane, not just the bottom left corner or the top right corner. So I would like to have points up here, right? And then I also use the minimum number of points. Practice, usually you need to have 15 points. And lastly, um, the pixel coordinates are not uniform. Like usually you have 640 by 480. The aspect ratio is not exactly 1. So we can deal with that by taking the points and then mapping them to 0 and giving them a variance of square root of 2, which simply changes the u and v points, coordinates. So that's what we do here. So I add more points. I now have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 calibration points. I can calibrate the points. And then oh, this is for some point here. Calculated. I just print out the UV for this probably. And then my calibration is much better. So now, basically any image, I can tell you exactly where that is on the cube. And the distance of the cube to the camera and all of that. And I don't have to do any measurement. I mean, the only measurements I have to do is in the image and the real world coordinates I have to do. So there, of course, it's helpful to have a regular object. Like the Rubik's Cube is great, right? It's very precisely built because otherwise you couldn't do all these rotations. And I can easily measure the size of the whole cube and I can figure out where the center points are. So this will be a very good calibration object. In this building, if I wanted to calibrate this room, that would be already hard. Right? I would need to know, I mean, I could measure the distance of this wall to that wall and assume that the walls are perpendicular and things like that. But it would be a lot harder. So often when we do calibration of cameras, we have a specific calibration object like the Rubik's Cube. If I want to calibrate the playing field for the soccer robot, I put the cube in, I take a picture of with the camera, I calibrate that camera, then I take the cube out. After that, I don't need the cube anymore. Then my robots can drive around there. Now, one thing that will happen is that here we now use the transformation matrix that results in the unit length. But the reason that's completely arbitrary in a sense, right? I just wanted to have one unique solution for my camera calibration. But I could have also said I don't like 1 as a unit length, I like 5.2. Then I normalize the entire matrix to give me a error of 5.2. It won't change anything in this particular particular image. But the actual values in the matrix would change then, right? And so one thing that happens is that if you look at the solution, here's the solution that we got for our 3 by 4 matrix, then the focal length is 127,000 centimeters, which would be an enormous camera, right? 127,000 centimeters is 12,000 meters, is 12 kilometers, which means the camera would be 12 kilometers wide, which clearly physically is not possible. But that doesn't really matter. It's just because I forced these constant to be 1, to add up to 1. So physically, that number doesn't work. So you couldn't go take your phone, take a picture, and then complain to Asus or iPhone saying you write the focal length is 3.2 millimeters, but my focal length is 12 kilometers. That wouldn't fly. But in practice, we don't really care about the focal length. Like, as long as this matrix gives us the right answer, we don't really care about the other parts of that matrix. Right? We don't care about the numbers that are here. We just care that if I put x, y, z, 1 on the right-hand side, I get the image coordinates u, v, ku, kv, and k on the left-hand side. That's the only thing we care about. Right? And that's what happens. So you can do some other fun things with this. You can measure the angle, calibrate the Leaning Tower of Pisa, for example, because you can look at the height and the diameter, and then check how many columns there are, then estimate what the positions of these columns are, how many floors there are, and then, yeah, I don't have a picture of it, but you can then project. You would be able to do a projection mapping onto the Tower of Pisa, assuming that you were in Pisa, and assuming that your camera is where you mount the projection, the LCD projection. Okay, good. So that's camera calibration. And Cubase. Now, if you look at the OpenCV library, there is a camera calibration routine, but that one, has anybody actually used it before? That one is slightly more complex. It's basically the same thing, doing the same thing. Most of it, what it's doing is doing the same thing that I'm doing here, except I mentioned that our lens is really not just one infinitely small point, but it is an actual lens. Like, it has some physical, even though it's small, it has some physical dimensions. It's also not flat, but it's like shaped like a lens, like an oval, right? Now, because of that, depending on what kind of camera you have, you get additional distortions, and especially if you have very wide angle lenses, like fisheye lenses and things like that, then the projection of a rectangle won't actually be rectangular. You get barrel distortion, and it'll look like this. We don't actually have a fisheye camera, otherwise I would show you in. So there's these kind of effects. So if you have a grid and you hold it up in front of the camera and your camera has a very wide angle, then it'll actually, sometimes it'll look like a barrel like this, or like a pin cushion, or like a mustache. And it depends on how far points are away from the optical axis, and it it's kind of tricky today because a lot of the cameras have some sophisticated algorithms for getting rid of this distortion as well, which is why you usually don't realize it or see it if you have a mobile phone or a standard webcam. The field of view is A, too small, and B, the processor inside of your CMOS chip already tries to correct for it. Now, these distortions we cannot model using a system of linear equations. They are actually modeled using cubic functions, so x to the power, cubic polynomials, x to the a multiplied by x cubed plus b x squared plus c x plus d. And if you look at camera calibration for OpenCV, it's actually done in 2 steps. The first step is to figure out what the focal length should be, because the focal length, unless you have a zoom camera, one that you can actually move the lens backwards and forwards, the focal length is fixed, right? It's always the same for the camera. The barrel distortion is always the same. And pincushion effect, all of this is the same. It doesn't change if you take a picture of this way or this way. It doesn't change. So these are called intrinsic parameters of the camera. There's also a couple of other ones, like the actual size of the pixels, like the aspect ratio of the camera is important, as well as the 0 point. Like here I said that the image coordinate is kind of 0, would be in the center of your image, right, where the optical axis is. But it's not always. So sometimes when they manufacture lenses, there is a little bit of error of that. So there are a couple of distortions that are nonlinear, so they can't be modeled using a system of linear equations. And they are intrinsic, which means they're always the same for the camera. It doesn't matter where you take the picture. So OpenCV, for the camera calibration, what they mean by camera calibration is actually just calibrating the intrinsic parameters, which is why if you look at the, have you ever calibrated the camera on our robot? No? My students never do. They really should, but we should use calibrated cameras. But anyway, the way that you do it is you hold up a checkerboard pattern, and then you just take a lot of pictures with it, all kinds of angles. And then you don't know anything about the position of these, so you don't need to know the size of the checkerboard or chessboard. You just hold it in front. That way, then the camera will model the intrinsic parameters. Focal length, pincushion, barrel distortion, and mustache distortion, as well as the center of your image, and aspect ratios. So that will be the first step. And in OpenCV, if you want to do this part, like what I did here, what's traditionally called camera calibration, if you want to be able to do that for a particular scene, the matching point things, then that's actually called a homography. So in OpenCV, you would use find homography in order to be able to do that. So in my system here, I mean, you can see this works quite well already without calibrating the camera and the pinpushing effect. For most applications, this will be good enough. If we think our soccer ball is 1 meter or 1.01 meters away, it doesn't really change the behavior of our robot. So for reasonable webcams, standard webcams, just doing this calibration is sufficient in many applications. If you have a wide angle lens or fisheye lens or some very specific application, then you need to calibrate the intrinsic parameters first and then the extrinsic. And if you do that in OpenCV, it's calibrate camera and find homography. And find homography is basically like this code. That's what that code does. And then, yes, so now you can map from 2D coordinates to, from 3D coordinates to image coordinates. And if you either know the distance to the wall, for example, by knowing the width of the wall, or any other kind of information, here with our climbing thing, okay, this will be bad. Before the camera panned up or tilted up here, you could see the floor, right? If you then say, oh, this Z coordinate, the bottom of this wall is Z0, and you can see it in the image, then you can also map all the pixels there. Right? Because you're only dealing with a particular plane here. Or, so whenever you make this plane here, you can say the Z coordinate will be 0. And this is X and Y coordinates for the angles. And then you're done. Then you can map from image coordinates to real world coordinates. Then you can send that to the robot. So this would work for that approach. Not for all climbing though, but all the climbing we'll be doing in this course. But like here, this would be a problem because for that particular picture, the wall is at an angle, right? It's not exactly straight up. So it goes like this, and then it changes to this angle. Then you cannot just assume that this x coordinate is 0. Like you can see, the thing is sloped out. That makes it three-dimensional. So then you need to use some other width of the entire thing. Or you know the height of some of the walls, for example. Anything. Yeah, like here, it's also not straight up. And it's not even a plane here. So calibrating that would be hard. Whereas if you know the points here, the width of this, and this Z coordinate is 0, then that. But yeah, I'm quite happy with this calibration. You can now try that yourself. Pick any calibration object and see if you can get, if you can map some coordinate system on top of it. Or you can try with the Tower of Pisa. Okay, good. And that's it for today. Also, remember today at 2, we have the class with the German students. Do your best to be there, at least virtually, because we need to set up the teams. Like you'll be matched with some German students. And then you can work with them on the vision part for the rock climbing rope. Okay. Any questions? Yeah. 2 o'clock, yeah. Okay, then try and join virtually. We will also post the recording for the class this afternoon, and you have to watch that yourself. Yeah. But today we're trying to set up the teams, the groups.
I thought we had our own group for next class, 2 p.m. We have our own group already.
What own group?
I mean, like, you have set the group before.
That was for assignment 1.
That's for assignment 1. So
Yeah.
every assignment has different.
There's only 2 assignments.
Oh, only 2 assignments.
Yeah.
Oh.
So the second assignment will be with the German students.
Oh, so it's different.
Different group, yeah.
Different group. Okay.
So who's in your group now?
For the next class, yes, because for this class we don't have any group.
For the next class?
Yeah, for the next class, Philip. From German also.
Yeah, yeah, okay. Yeah, so we have some German students that just happen to be here from the same university that we're collaborating with now. So some teams have already grouped. So we'll see. I need to know how many we have on the German side.
Because Philip worked with me to build that robot, that leg.
Yeah.
So that if I have to take a new group.
But you don't have to build a new leg.
I mean, we have to share the leg with
You
Philip.
would have to share the leg.
Yeah.
So we'll see how it goes.
Yeah. Okay.
Ideally, we'll have groups of 4, so join. So it's just the 2 of you so far, right?
Yeah. So we still can have with the same team.
Possibly.
The last assignment. Okay.
And yeah, look at it as an opportunity. It's fun to work together with students from different countries.
And also for your assignment, do we have to create 2 reports even we are in the same group, or 1 report per group?
1 report, you co-author the report. That'd be crazy nowadays to ask for 2 reports. Then I just get 2 students putting it into ChatGPT, giving me 2 versions.
It's very easy to create the report. Just let ChatGPT help us.
Yeah.
And then
as long as you specify it in your honesty file, that's correct. In your honesty declaration, you would be allowed to do that. Okay, good. Then where am I here? Oh no. Oh no. Yeah. No. Okay. It's too late.